All right. Yeah, welcome. Good morning, everyone. Thank you for joining our SDSU TILOS seminar here, and thanks to those on Zoom as well. It's my pleasure to introduce Professor David Rosen, who's an assistant professor in both the departments of electrical and computer engineering and the Department of Mathematics at Northeastern University, where he leads the Robust Autonomy Laboratory. Before Northeastern, Professor Rosen spent time as a research scientist at Oculus Research and as a postdoc at MIT's Lab for Information and Decision Systems. He's broadly interested in mathematical and algorithmic foundations of trustworthy machine perception, learning, and control. And today he's going to talk about certifiably correct machine perception. I'll just ask that we hold questions in the room until the end of the talk. And if you have questions on Zoom, go ahead and type them in and I'll take care of that.
Okay, thanks very much. Well, thanks for the invitation to speak. It's a pleasure to be here. And yeah, I'd like to tell you a little bit about some of the work that my group and I have been doing over the last few years in the general area of what we're calling certifiably correct machine perception. So by way of motivation, I would describe myself as a roboticist. And while there's some debate over what the exact operational definition of robotics is, the one that I like is that robotics is really the science of physically embodied autonomous agents. And if you think about, okay, well, what does that mean? What are the core capabilities that we want physically, embodied autonomous agents to have? Things like planning, navigation, manipulation, all those core competencies really require accurate geometric models of the environment in order to work. And so if you think about what that, what does that entail? Well, okay, well, let's see, if you imagine that we're an autonomous vehicle driving around doing stuff, what are the kinds of models that an autonomous vehicle would need in order to operate correctly, right? What I'm showing you here is sort of the internal robot eye view of the world, so to speak, for some autonomous car that's driving down some road here. And the main thing I just want to point out here is, if you look at all of this, there's just a lot of stuff that's going on in the environment that this vehicle has to be able to estimate, right? It's got to keep track of where it is on the road. It's got to be able to identify lane markings, pick out stop signs, figure out where other vehicles are, other cyclists, pedestrians, etc. And so there's a ton of stuff going on in the world around this vehicle that it's got to be able to keep track of. And it's got to be able to do all of this stuff both quickly, because it's got to be making decisions in hard real time, and it's got to do it reliably. Because you could imagine, for example, if I fail to recognize that there's a cyclist there, or I misclassify a stop sign as like a 30-mile-an-hour sign, somebody's going to have a super bad day, right? And so, so the punchline here basically is there's a lot of stuff going on. It's got to be estimated very precisely and very quickly. Okay, so I've used this word perception now, and really what I mean by that, just to ground the talk a little bit more, is really anything that sits between raw sensor data as input and some model of the world that our robot's going to use for downstream decision making. And so, there's many different ways of operationalizing this mathematically, but if you were to go into the robotics literature or the computer vision literature and pick up some paper that's talking about this, the kind of thing that you would see is a problem formulation that looks like this. It's really an optimization-based method. And so the idea here basically is we've got some bit of data that's coming off of our sensor, laser scanner, et cetera, right? We've got some parameters that model the state of the world that we're trying to estimate. So these would be things like, the position of the robot in the world, the position of pedestrians that we might see, et cetera. And we have some loss function that essentially measures, if I plug in the data that actually came off of my sensors, and I plug in some hypothetical model of the world, what this loss function is measuring is how well does that hypothetical model of the world explain the data that I actually got? What's the mismatch between this hypothesis and the data that I actually have in my hand? And so the idea then is, in terms of doing estimation, what I want to find the estimate of these parameters that minimizes the disagreement between my model and the observations that came off my sensors. And so, for those of you who've studied statistics, you might recognize this as maximum likelihood estimation falls into this. Regularized empirical risk minimization falls into this for those of you who are doing machine learning. So neural network training is an example of this and so on. Right? So pretty much, across ML, robotics, machine learning, computer vision, this is the sort of thing that you're going to see. Okay, so that's great. So if you open up one of these papers, this is the kind of thing they're going to ask you to do. And so why is that problematic? Well, it's problematic because that's about as far as those papers go. They say, just solve this optimization problem, you will get the answer, and then you're good to go, right? But I claim that there's actually quite a bit of complexity being concealed in this relatively innocuous expression And the reason for that is that, it turns out that many of the optimization problems that we want to solve in order to do geometric estimation, like robotic mapping, navigation, et cetera, require solving optimization problems that are both high dimensional, just because there's a lot of states that you want to estimate. So if you imagine, I do a lot of work in robotic mapping. If you imagine how many parameters would I need to describe like a building of this size, it's a lot of parameters there, right? So it's a high dimensional estimation problem. And it's also non-convex, in part because a lot of the parameters that we want to estimate belong to non-convex parameter spaces. So for example, this is true anytime you're estimating an orientation, for instance, right? These orientations are a non-convex set. And so you can imagine if I want to fly my drone somewhere, being able to distinguish if the drone is like this versus like this, is kind of important. Is the drone right side up or not, right? And so pretty much any realistic robotic estimation problem is going to involve non-convex configuration spaces. And okay, well, what does that mean? Well, anytime you're looking at an optimization problem that is both high dimensional and non-convex, there should be alarm bells that are going off in your head, because these problems are almost always hard in the sense of computational complexity theory. And in particular, almost all the problems that show up in the context of robotic spatial perception that we're interested in solving in real life can be shown to be NP hard at least. And so then you might say, okay, Dave, well, we solve hard optimization problems all the time in machine learning. Is this really a big deal? And I claim actually that it is, because the kinds of problems that we're interested in robotics tend to have a really adversarial loss landscape, which is in marked contrast to the kinds of things you might see if you do, for example, over-parameterized neural network training. And so just to give an example of what this looks like, to make it concrete, what I'm showing you here is what would be considered a relatively simple example of trajectory estimation in robotic mapping and navigation. And so this is an actual data set that was collected by the Stanford autonomous car. And what this car did is it started down here in some parking lot, drove up along this road into this parking garage, and then up and down these ramps as it was exploring this parking garage. And the object of this estimation exercise is to determine what is the trajectory that this robot went through as it was doing that data collection. So what I'm showing you here is the actual optimal solution to this estimation problem that corresponds to this particular data set. So as you can see here, you get a pretty nice estimate of the robot trajectory. You can pick out the internal parking ramps in this parking structure. Okay, so what happens now if I just do the sort of naive thing that I would expect for non-convex optimization, where I just pick some starting point, I throw a gradient descent at it, and I just run downhill in the usual way, right? What are the kinds of things that I might discover? Well, here's an example of the kind of thing that you can get, right? And so, in contrast to the case of neural network training, where these things are very over-parameterized or in the very high data regime, that is not the case for the kinds of estimation problems that we see show up in robotics. And so this is the kind of stuff that naive estimation methods of that type will return to you. And so I just want you to imagine for a moment that you're in your autonomous car and you're driving down the Autobahn at 120 miles an hour, right? And this is the map of the world that your robot is using in order to make decisions about what to do, right? This is the kind of thing that keeps me up at night, right? So, this is like really bad, right? Like we do not want this to happen, right? And so the real sort of high-level question that has been motivating a lot of the work that my group has done over the past few years is, can we develop estimation techniques that on the one hand are tractable, they're computationally efficient enough that you can run them in hard real time on lightweight, resource-constrained mobile platforms, but on the other hand, also enable you to say things about safety and quality of the solutions they are going to return to you, because we want to use these estimates in order to control, expensive, potentially dangerous cyber-physical systems like autonomous vehicles. So that's really sort of the top-level question that's motivated a lot of my group's research. Okay, so bearing that in mind, the main idea that I want to convey to you today is that convex relaxation provides a powerful approach for building fast, global optimization techniques to solve challenging estimation problems in practice. And so in particular, what I'm going to show you today is that this actually enables the recovery of provably globally optimal solutions to many challenging estimation problems under realistic conditions. Not only that, but if you're sufficiently clever about how you solve these convex relaxations, you can actually do so with a speed that actually matches or exceeds existing heuristic local search-based methods. And so the combination of those two things together then gives you both a principled and a practical approach to achieving provably robust, safe, trustworthy machine perception. So that's what we're going to talk about today. So the remainder of this talk, I'm going to use robotic mapping as sort of a motivating, concrete example, just to make some of this stuff a little bit more concrete. So I'm going to give you a light introduction to sort of the mathematical formulation of what robotic mapping and navigation looks like. I'll then show you how we can produce convex relaxations for that problem. and then I'll describe how we can design fast optimization techniques to solve those resulting convex relaxations quickly. Okay, so for those of you who have not seen robotic mapping before, maybe you're not familiar with exactly what this problem formulation works, I thought I'd start with a little sort of cartoon introduction to just give you the mathematical setup for what this looks like. So let's suppose we've got some robot, and we want this robot to be introduced into some environment that we don't already know. We want it to run around and sort of create some map. So, this robot's going to be inside this environment. It's going to go through some sequence of poses, and it's going to be sort of collecting a bunch of data along the way. Now, one thing that you might notice is, cameras can't see through walls, lasers can't see through walls, lasers have limited fields of view or sensing range and so on. And so at each location in this environment, this robot is only able to see, to collect information about a relatively small portion of the environment at a time. And so if you look at sort of what is the actual raw data that comes off of my robot's sensors, it just looks like a stack of little cross sections, little segments of the environment that I've seen as I've been driving around. And that's literally the data that you have access to, is just sort of a stack of local cross sections. Now, if I actually knew the trajectory, that is the sequence of positions and orientations that my robot had gone through as it was doing this data collection, I could imagine taking each of these individual scans and sort of attaching it to the pose from which it was collected. And if I were to do that, the effect of that would be I would sort of unfold or co-register all of these individual scans into a common coordinate system that would then give me a coherent reconstruction of the environment that I had traversed as I was doing this mapping. And so that's what I would like to achieve. The catch here, though, is that I don't actually have any device that will directly tell me what the sequence of poses was, right? GPS doesn't work indoors. Even if it did, I still need to know the orientation of the robot and so on, right? And so the question then becomes, how do I do this trajectory estimation? So the way that this is, I'm going to give you the super abbreviated version, but the way that this is done operationally is the following. Let's suppose that I look in the environment and I see some landmark, like that chair over there, that shows up in one of my scans. And then my robot moves, and I collect a second scan, and I can see that same landmark in that second scan. That landmark is going to show up in two different locations in these two scans that I have collected. And if I think about why that is the case, what is really going on is that the apparent motion or the shifting of the location of that landmark in those two scans is actually caused by the motion of the robot itself. And so what this means is that if I think back through this collection of scans that I've collected so far, anytime I see the same object, or I can recognize that I'm looking at the same object across multiple different scans, that recognition tells me something about the relative motion that that robot underwent between when those two scans were taken. And so what that means is that by searching for these common landmarks, I can effectively estimate the relative motion between pairs of unknown scans that I'm trying to, whose values I'm trying to estimate as part of this trajectory estimation problem. So a little bit more abstractly, what this means is that as the robot is sort of driving around, it's building up this network of unknown poses and estimated noisy relative motions between these unknown poses as it's exploring. And so we can sort of imagine organizing all this data into a network of noisy spatial relations that we often call pose graph in robotics. Okay, so the mathematical formalization of robotic mapping then is what's called pose graph SLAM. And basically, so the setup for this problem is we're trying to estimate a collection of unknown poses, which are in one-to-one correspondence with the vertices of this graph. We are given a set of estimated noisy relative motions between these unknown poses, which are attached to the edges in this graph. And the goal of this problem then is we want to figure out, okay, what are estimates for this unknown sequence of robot poses? What's the trajectory estimate that best explains this network of noisy spatial relations? And under a suitable noise model, which I'm not going to get into, so just take my word for it, you can read the paper, we'll explain exactly how you arrive at this, but under a suitable noise model, one can show that you can formulate this estimation problem as a maximum likelihood estimation that looks like this. And the main thing I want to point out here is just that the objective here is pretty nice. It's just this totally standard linear least squares objective on the rotation states for your poses and the positions for your poses. So that's all fine. But this problem is high dimensional because I might need to collect many, many scans to map out a building of this size. So I have to estimate many poses. And it's non-convex in particular because we're estimating robot poses which contain orientation states, and therefore the parameter space is non-convex. And in particular, not only is it non-convex, but you can show that this specific formulation of this problem is in fact NP-hard. So that's not great. Yeah, question.
And the kappa ij is some form of importance criteria?
Yeah, that comes from the precision of the measurements that you're sampling in this case. Yeah, thank you. Those are precisions for those measurements. Yeah, so this particular problem formulation is NP-hard, which is not great because this is the thing we actually need to solve, right? So I'll just say maybe as a quick aside, so that's postgraph optimization. And if you think about what sort of is really going on there, really postgraph optimization is really sort of modeling this idea that I want to construct a globally consistent reconstruction from local observations of some environment, right? And that motif shows up all over the place in spatial estimation or machine perception. So while we're interested in solving postgraph optimization for robotic mapping, it turns out that problems of exactly this form or very similar ones show up all over the place in machine perception or spatial estimation. And so in particular, it's fundamental to robotic mapping. It shows up in 3D reconstruction, computer vision. It's useful for multi-sensor recalibration if you're going to have a multi-sensor sensor platform. And closely related problems show up in classical sort of information theory or state estimation. Max cut, which is a very famous problem, is actually a special instance of this problem, as is, and there's a closely related one in cryo-electron microscopy. So for those of you who might be interested in small molecule biology, for instance, you actually end up doing very, very similar things when you're processing electron microscope images of small biological molecules. So this problem is hard. But if we're able to make progress on it, actually that has ramifications for all these different areas. We can actually figure out how to solve this problem reliably in practice. Okay, so how are we actually going to do that? So, well, the main idea behind our approach is, we shouldn't expect to be able to solve, NP-hard estimation problems efficiently in general, unless you're a true believer that P is NP and quantum computers are going to solve all our problems for us, which I personally am not. So that maybe initially seems discouraging. But if I stop and think for a second, I might realize that concluding phrase there in general is actually doing a lot of work in this sense. And the reason for that is that NP hardness is really a worst case adversarial notion of computational complexity. And so all it says is that if you give me some problem class and you give me an algorithm you claim can solve every instance of a problem in that problem class, I can reach into that problem class and I can pluck out one or a handful of challenging instances that have to make your algorithm work super hard. Do something like exhaustive search over an exponentially large search space. But that doesn't say anything about the prevalence of those hard cases in this overall problem class. And so what we might hope notionally is that perhaps there is some kind of separation between these totally crazy adversarial problem instances that we might conceivably get and the actual real life instances that come off of our actual sensors when we're trying to solve problems in actual engineering applications. And that, so maybe, we might, if somehow, if the problems that we actually care about are an easier subset, maybe we can somehow well approximate these in some suitable fashion, right? Efficiently. And so you might say, okay, well, that's a nice cartoon you got there, Dave, but, how am I supposed to actually operationalize this, right? Like, how do I, even if that were true, how would I do something useful with it, right? So the main technique that my group has been getting a lot of mileage out of recently is something called convex relaxation. And the idea of it here basically is instead of trying to solve the original problem, what we're going to do is we're going to solve a convex approximation. And so this is kind of nice because oftentimes there's standard machinery for constructing these, which I'll talk about momentarily. And because it is, convex optimization is super nice, it's a lot easier to analyze properties of convex optimization problems than it is to analyze properties of non-convex ones. These convex relaxations themselves often admit formal guarantees on the quality of the approximate solutions that they return, which gives you a way of solving problems both fast, because convex optimization is a lot easier, while still preserving some kind of safety and performance guarantees. So it turns out that this picture is in fact correct. This actually is what the actual problem landscape looks like, and I'll show you how we establish that result presently. Okay, so the specific setting or the specific setup that we're going to take advantage of is we're going to consider the class specifically of what are called polynomial optimization problems. And so for those of you who have not seen these before, it's actually pretty much exactly what it sounds like. A polynomial optimization problem is just a problem in which the objective and the constraint functions turn out to be polynomial equations. So we have a polynomial objective, polynomial equality, and inequality constraint. And so this is kind of nice because, as it turns out, there's a ton of machine perception problems that can be formulated in this way. That's great because it's a very flexible modeling class. It's perhaps less great because this modeling class is so broad, it encompasses tons of problems that are also NP-hard. And so overall polynomial programming is at least NP-hard to solve. So, okay, that makes sense. So why are we interested in this particular class? We are interested in this particular class because the condition of being a polynomial is a global condition, right? You're only a polynomial if you're a polynomial everywhere. And so even though this is a very general problem class, it's quite flexible, the condition of being a polynomial is actually still enough that it gives you some kind of global control over the behavior of these optimization problems, which is the thing that we need to produce effective relaxations. And in particular, POPs admit a standard family of convex relaxations called moment relaxations, which is the specific gadget that we're going to take advantage of, and which I'm going to show you on the next slide how to construct. Okay, so this is going to be probably the heaviest math slide in the talk, so just bear with me here and I'll walk you guys through this. So, okay, so let's suppose that we have a polynomial f that is going to be in n variables. And that this polynomial is going to have a degree, it has degree d. So what we can do is we can write down every monomial term in the variables x1 through xn up to and including degree d. And so there's going to be a ton of these. There's going to be exactly n plus d to choose d of them. But whatever these things are, we can imagine just concatenating all these things into a big vector. Okay. So if we do that, then there is going to be some associated coefficient vector that literally just says, okay, this is the coefficient of the corresponding monomial term in that polynomial. Okay, so nothing magic has happened yet. It's just what polynomials look like. Okay, so here's where sort of the first non-trivial bit is here. Okay, so let me take half the degree of my original polynomial f and round it up. And I'm going to call that number p. Okay, and I'm going to choose n to be the number of monomial up to and including degree p in that same basis. So I claim that there exists some symmetric matrix f such that I can represent my original polynomial f as some quadratic form that is parameterized by this symmetric matrix f. Now, this may not be immediately obvious why this is true, but it turns out it's actually just a very simple trick, which is just, if I have all these monomials up to degree d over 2, and I multiply them all together, that is going to generate all monomials up to degree d, because I'm squaring things that are up to degree d over 2, right? And so because of that, it's not too hard to see that I can always reproduce all of the original terms up to degree d that I had in my original polynomial. That's basically all that's happening. So this is just a pretty basic geometric or little algebraic trick here. So while this is not complicated, it actually already has a couple of interesting properties, though. And so the first thing is that, if I look at how this coefficient vector and this matrix are related to each other, this is actually just a linear relation, right? Because the monomial terms themselves are just coefficients. So what that tells me is, in particular, if you give me an original vector, just a coefficient vector of a polynomial, I can easily compute and return to you an associated f. Okay, so that's observation 1. Observation 2 is that if I look at the right-hand side of this equation here, this form, this outer product is just an outer product of vectors, right? So it's a symmetric rank 1 positive semi-definite matrix. Okay, that's observation 2. And that's basically all you need to come up with the concept of moment relaxation. All moment relaxation is just, if you understand that you can perform these simple algebraic transformations, all moment relaxation is, notionally, essentially, is we're going to take this rank 1 symmetric outer product, and we're just going to replace it with a generic PSD matrix S of appropriate size. That's it. That's the entire trick. Okay, so what does that actually look like operationally? What this looks like operationally is I'm going to start with a polynomial optimization problem, which is some crazy high-dimensional nonlinear thing. I'm going to perform moment relaxation. And what I get then is a resulting problem in which I have a linear objective now and linear equality and inequality constraints, but where the decision variable now is a high-dimensional PSD matrix as opposed to a vector of individual scalars. Okay, so why is this useful? Well, the first thing that I can see is that I immediately get, if I can solve this problem, I immediately get a lower bound on the optimal value of this problem. And that's just because literally every one of these outer products of monomial vectors gives me a PSD matrix that looks like this. But there's a bunch of these PSD matrices that are not symmetric rank 1, right? And so effectively what I can think of is what this relaxation does is it essentially takes the decision variables over here and lifts and embeds them into a much higher dimensional space in this relaxation. And so because I'm minimizing essentially the same function over a much larger set, I can always achieve an optimization value that is an optimal value that is less than the one that I started with. I can always do better, or at least as well, because I'm minimizing the same stuff over a larger set. So that's relatively straightforward. Second thing is that this is an optimization problem in which the objective and constraints are linear equalities and inequalities, and the decision variable is part of the PSD cone. Both of those subsets are convex. The PSD cone is convex. Linear equality and inequality constraints gives me linear half spaces and linear and hyperplanes in my feasible set. And so what that means is this moment relaxation is a particular kind of convex program called a semi-definite program. And those are convex, and it's known how to solve those to global optimality efficiently using off-the-shelf tools. And then finally, the part about this that is going to be of interest to us is, this is the interesting bit. Suppose that I were to solve this STP, this moment relaxation. And it turns out that the minimizer that I get happens to be a rank 1 matrix that that can be factored as a product of things that look like these monomial vectors. If that is the case, I can immediately conclude that this resulting vector that comes from this rank 1 factorization in fact provides a globally optimal solution to my original problem, because it is a feasible point and it attains equality between this lower bound. And therefore that actually, not only do I get a minimizer, but I get a computational certificate that that thing is in fact a global minimizer. So not only do I get the right answer, but I can recognize that I've gotten the right answer, which, as you can imagine, is extremely important for the safety critical applications that we want to use these tools for. It's not just knowing that you're not just getting the right answer, but knowing that you got the right answer, or didn't, as the case may be. Okay, so why am I going to tell you all this? I'm telling you all this because the remarkable fact that justifies our interest in this particular relaxation strategy is that this favorable case, where this relaxation is exact, actually frequently occurs for many of the machine perception tasks that we are interested in solving operationally. And so what this gives us then is a way of actually solving these many instances of this really hard machine perception tasks that are in general intractable by means of efficient convex relaxation. So this is operationally how our techniques are going to work. Okay, so overall then, bearing all that in mind, this actually suggests a fairly direct sort of general recipe for constructing trustworthy machine perception algorithms. I'll give it to you. It's just 3 easy steps. Step 1 is write down your estimation problem as a polynomial optimization problem. Step 2 is apply some kind of convex relaxation, could be Lagrangian, could be moment relaxation, to produce a relaxation for your original problem in the form of, in our case, usually an STP. And then step 3 is just try to argue, either theoretically or empirically, that this relaxation turns out to produce solution, turns out to be exact under operationally, usually bounded noise. So we actually have some formal guarantees that certain classes of these STP relaxations will in fact produce exact results under moderate levels of measurement noise. And I'll show you an example of that momentarily. Okay, any questions on this general sort of framework so far? Nope, okay. Okay, so I'm going to go back to our PGO example. I'm going to show you exactly how this applies to that specific concrete instance. So just to recall, here's our objective for our postgraph optimization problem. Before we get to the relaxation, I'm going to show you one very brief algebraic simplification you can make to this. It's just going to simplify the problem a bit. And that's just to observe that if I look at how the translational states enter this, if I just fix some arbitrary rotational estimates, and I think about performing partial minimization over only the translational states, what I might notice is that this problem now just looks like totally vanilla, unconstrained, linear least squares estimation. We know exactly how to solve that. We can do it in a closed form using matrix factorizations. And so what that means is that if I fix an estimate for the rotations, I can solve for a corresponding optimal value of the translations using matrix factorizations, in this case, a generalized short complement. And so what that means is that I can write down an optimal choice of the translations as a function of the rotations, and that optimal choice will turn out to be linear. It'll be linear in the rotations. And so what I can do then is I can simply take that optimal assignment and plug it back into this objective. And what that will do is it will analytically eliminate the translational states from this problem and leave me a corresponding problem that I can package up into a nice quadratic form that looks like this, that now only involves just the rotational states. And so I think of R here as being a row matrix that has rotation matrix blocks in it. Okay, so that was just a bit of a minor algebraic simplification. What is the utility of that? The utility of that is that I now have a nice compact algebraic expression for my optimization problem. Okay, so this is the slide where the magic happens. Now we're going to show how we derive our convex relaxation. Okay, so if I stare at this, what I might realize is that this is a nice convex quadratic form here. So the only difficulty is the fact that these R's are constrained to be, row matrices of rotations, which is a non-convex constraint. But if I think a little bit about, okay, how do these decision variables actually enter this problem? Well, they only actually enter this problem through this outer product R transpose R. And so if I think to myself, okay, well, what does R transpose R actually look like? Well, I mean, as we saw before, it's a PSD matrix because it's a symmetric outer product. It's a row matrix that has rotation matrices inside of it as blocks. And because R transpose R is the identity for any rotation, it's going to have a block diagonal that is comprised of identity matrices. And so in this case, one can show that this moment relaxation simply consists of, or a moment relaxation simply consists of, if I look at the right-hand side here, well, again, this is a PSD constraint. This is a linear, having an identity matrix or a block, having a diagonal, block diagonal that is comprised of identity matrices is a set of linear constraints. And so again, everything that's on the right-hand side here, it lies in the intersection of the PSD cone with a particular linear subspace. So that is to say, the stuff in braces here on the right-hand side is a spectral hedral set and therefore convex. And so we're going to do the same trick that we did before, which is I'm simply going to replace every instance of R transpose R with a generic PSD matrix of appropriate size that has the specified block diagonal structure. And that's going to be our relaxation. Okay, so what we have then is our original simplified PGO problem, our relaxation on the right. Why are we interested in this particular relaxation? We are interested in this particular relaxation because of the following theorem. So this is the main result from our initial paper on this, which was published in Wafer in 2016. And there's a bit of there's a bit of text here, so I'll just kind of walk you through this. What this result says is that this matrix Q is a data matrix that is parameterized by the relative motion estimates between edges of my graph. So this is purely comprised of data. And so in principle, if I look at any ML estimation problem, there is in principle some ground truth configuration that is out there that I don't have access to. This would consist of like noiseless measurements, perfect measurements, for example. I don't know what those are, but there is one that is floating around in the ether, at least in principle, right? And so what this theorem says is that if the actual measurement matrix that I get, the actual noisy measurements that I get, if the data matrix that is parameterized by those noisy measurements is not too far away from this idealized ground truth noiseless data matrix, then, that is to say, if my measurements are not too noisy, then this semi-definite relaxation has a unique solution. And that unique solution factors in exactly the way that is necessary to recover a minimizing set of estimates for my original PGO problem. And so the practical payoff of this then is under this condition, whenever this relaxation is exact, we can recover a global minimizer to our original NP-hard optimization or estimation problem by solving this semi-definite relaxation. So we can solve a convex program and we can recover a solution to an NP-hard or generically NP-hard state estimation problem by means of solving that convex relaxation. So that is the approach that we're going to take. Any questions on that?
Is there any loss of rigor on this part because of kind of the bootstrapping in the beginning of kind of fixing R and optimizing T and then just working with R? Like,
No, there's no loss there. That's an exact statement. There's an exact equivalence between these two problems.
okay.
So yeah, and the equivalence is just that, you know, once I know what R is, I can go back and I can recover the corresponding T when I'm done.
Okay.
Yeah.
Thank you.
Yeah.
My question is very straightforward, just double checking. I presume that you're gonna use the relaxation under like a Lagrangian form, right? Because you have the constraints.
Oh yeah, so we actually derived, so this is the actual relaxation itself. We actually got this particular one, we derived it via Lagrangian relaxation. It's just a little bit easier to, so we didn't derive it the way that I presented it. I just presented it this way because it's a bit more direct to see. This is actually the double dual. So if you take the dual of the dual, then you get this one. But if this is a little bit more direct to see why it's the way that it is, so to speak, yeah. Okay, so in principle, what that theorem tells us is that all we have to do is just solve this relaxation and then we're done, right? We get the answer. So that's great. So now I'm just going to take my favorite, you know, interior point method for STP, and I'm just going to plug it into the, you know, plug this relaxation and then solve it. Right? Well, not quite. Okay, so what I'm showing you here is the computational cost of solving a simple simulated little map problem involving a robot navigating around edges on this cube. And what's being shown here is the number of poses on the side of one of this cube, right? So the punchline here basically is this is a mapping problem involving on the order of about 200 or 300 poses. And we can see that solving this STP relaxation using a standard off-the-shelf tool is requiring something like, you know, 1,000, 1,200 seconds to solve, right? So this is like, you know, 20 minutes. Okay. To give you a sense of scale, for those of you who have not had a lot of experience with robot mapping, in order for this approach to be practically useful, I would have to solve a problem that is about 2 orders of magnitude larger than this. And I'd have to be able to do that on the order of about a second or less, fractions of a second, in order for this to be practically useful. So this is not even close to being competitive, right? And so you might say, okay, well, like, why is it that this is so slow? Well, I mean, if you think back to how we produced this relaxation, you know, we took this outer product, right, which basically involves, you know, taking a problem of dimension n and embedding it into a higher dimensional space of dimension n squared. So I'm blowing up the problem by a factor of n, the decision space that I'm searching over, right? And if n is 60,000, because I'm estimating a high dimensional map, right, I've made my decision space 60,000 times larger. So maybe it's not surprising why that would be slow, right? And you know, basically, you know, what you can work out is, while STPs are efficient in the sense of computational complexity theory, meaning the polynomial time solvable, right? The actual exponent that is on that polynomial is like n to the 6th. So if I blow up my problem by a factor of 10, I've made it 1,000,000 times harder, right? Well, we need to be 2 orders of magnitude larger than what's being shown here, and we need to be about 3 orders of magnitude faster, right? Which means that in order for this to be operationally useful, I have to solve problems that are about 10 to the 12 orders of magnitude, that are about 12 orders of magnitude harder, and I've got to do it about 1,000 times faster than what is being shown on this plot in order for this to be practically useful. So that's not good. That seems tough. So how are we going to do that, right? You know, in keeping with this idea that maybe we don't want to try to solve every problem, right? We just want to solve those problems that we particularly are interested in for engineering applications. Perhaps we might think that it's possible to build a specialized solver that is somehow structure exploiting that would enable us to solve these large-scale STPs a little bit more efficiently than sort of general interior point off-the-shelf tools can. So that's what we're going to talk about now. And the main trick that we're going to use to do this is a technique called Biermann-Terra factorization. And so the idea here is, for those of you who have not seen this before, is that Biermann-Terra factorization is an optimization technique for semi-definite programming that enables you to exploit the existence of low-rank solutions for an STP. And if you think back to that theorem that I showed you earlier about the exactness of this relaxation, what that theorem shows is, in fact, that the STP relaxations we have in mind do, in fact, have low-rank solutions. In fact, it has a unique solution and when it's exact, and the rank of that solution is exactly D, irrespective of how big the problem is. So if I'm solving a 2D optimization problem or a 2D estimation problem, the rank of my STP solution is going to be 2, or 3 in the case of three-dimensional mapping. Okay, so how does Biermann-Terra factorization work? Let's suppose that I'm looking at an STP, and I know that that STP has a solution of rank, let's say R. So solution of rank R. If I know that that is the case, or I'm willing to make the bold assumption that it is the case, all I do is I simply replace the decision variable in my original STP with an assumed rank R symmetric outer product that looks like that. So I'll just replace every instance of that in my original STP with an assumed rank R symmetric factorization. Okay, so what does that get me? It gets me a couple things. I mean, if the rank of my solution is much, much less than n, then the dimension of my search space for this problem is way tinier than the dimension of my search space over here. Right? So that's already my problem is way more compact to write down. Secondly, it's not too hard to convince yourself that as long as I pick this rank parameter R sufficiently large, any minimizer over here can be represented by an associated low rank factorization over here. And therefore, if I solve this problem and I find a global minimizer, y, that global minimizer actually gives me a low rank factor for a solution of my original STP. And so what that means is I can search for solutions of my STP by applying nonlinear programming methods over here. And then this third observation, of course, is just that unlike STPs, which have this positive semi-definite conic constraint, the only constraints over here are just equality constraints in this formulation. And so this Vieira-Montero factor problem is just a standard nonlinear program, which we can solve at least locally using totally standard off-the-shelf, just nonlinear programming methods, your favorite nonlinear programming library from MATLAB, IPF, or whatever, or what have you. Okay, so those of you who've been following along so far might be saying, okay, well, but what does this actually get you? Because yeah, this is low rank and stuff, but it's now also a quadratic constraint quadratic program, right? And so now it's non-convex again, and the whole point of this, what you started telling us about, is that you don't want to solve non-convex problems, right? So I agree that you can do all of this, but what is the actual practical utility of doing this transformation now, right? Okay, so it turns out that even though So we can solve these low rank nonlinear programs, but because they are non-convex, the question then becomes, what happens if you find a local solution? How do you tell if it's actually a solution to the STP or not? And if it's not, what do you do, right? Because it is possible you can get stuck in a local minimum here, right? Okay, well, let's sort of consider then, if I were to apply just a totally vanilla local nonlinear programming method to this Vieira-Montero factored STP, I can find some local minimizer at least, but then what does that get? Okay. Well, maybe the first question we'd want to consider is, when does a local minimizer actually provide a solution to our original STP? Okay, so to answer that, we can imagine just literally just writing down the KKT conditions side by side for this pair of problems. And so if you do that, just as a convenience, I'm going to define a certificate matrix in the following way. So this is going to be a Lagrange multiplier for a solution of, let's say, this Vieira-Montero factor program, STP. So if I apply local minimization, I get both an estimate y star and I get an associated set of Lagrange multipliers for the constraints that are in this problem. And using those Lagrange multipliers, I'm going to define a corresponding certificate matrix that is constructed from that Lagrange multiplier vector and the matrices that describe my original, define my original STP. So that's just the definition. Okay, so with that definition in hand, if I look at the KKT conditions for my two problems, the necessary conditions for this non-convex problem are that the product of the certificate matrix and Y has to be 0. For the corresponding semi-definite program, the conditions are both necessary and sufficient because it's a convex problem. And they look like this. The certificate matrix here plus Z times Z has to be 0, and the certificate matrix has to be PSD. Well, if Z is Y transpose Y, and I already know that S times Y is 0, then certainly this also holds. If I take as my estimate Z is Y transpose Y. So this is guaranteed to hold. So the only thing that remains is just to show that this certificate matrix has to be PSD. That is to say, all I have to do is just check whether or not this certificate matrix that I can build from a local solution to my STP is positive semi-definite. And if it is, then I know that this is a low rank factor for a solution to my STP, and I have solved my problem. Okay, so that's great. I can at least recognize when this has worked. The next question you might ask might be, okay, but what if it doesn't work? Like, what if I check that positive semi-definiteness condition and it turns out that it's not positive semi-definite? What do I do then? Turns out you can actually take this one step further and prove a really nice theorem of the alternative. And so what this theorem basically says is, if I solve this problem and I find a KK2 point where the linear independence constraint qualification holds, then there's going to be exactly one of two cases that are going to be true. Either I construct the certificate matrix and it's PSD, in which case, great, I know that I've solved my problem. I've found a solution to my original STP. Or this certificate matrix is not going to be PSD. And in the event that it is not PSD, I know that it has to have some direction of negative curvature. There's some vector that is a vector direction of negative curvature for this matrix. And if I take that vector, I can actually use that vector to construct a second order direction of descent from the solution that I have in my hand, embedded into the next higher dimensional relaxation or next higher dimensional rank restriction for my Beer-Montero factored STP. So I increase R by 1, the assumed rank of my solutions, I increase by 1, and I can construct, using that direction of negative curvature, a direction of descent, second order direction of descent from that lifted solution that I have in my hand. And so what that allows me to do is it actually allows me to continue optimizing by searching for an improved solution to my STP, an improved low rank factor for my STP. So this is kind of nice, because what this gives me then is it gives me a theorem of the alternative. Either I found that I have an answer, or I get a direction of descent that enables me to continue my search. And so what this leads to then is a super nice method for performing low rank semi-definite programming that looks like the following. All I do is you give me some initial starting point, which is just a candidate low rank factor for a solution of my STP at some initial assumed rank restriction, R0. And I just repeat the following. I just take that, starting at that initial estimate, I just apply second order, or my favorite local optimization method to this Beer-Montero factored STP, just whatever off-the-shelf optimization technique I have in hand. That's going to give me some, KKT point, so I get an estimate together with a Lagrange multiplier. I just construct this corresponding certificate matrix that we saw before, and then I just simply compute a minimum eigenpair for that matrix, and that's just totally basic linear algebra, right? That's just stuff you've been doing since you were in freshman linear algebra, right? And then I simply inspect what is that corresponding minimum eigenvalue. And if that minimum eigenvalue is greater than 0, that theorem tells me that Y is a low rank factor for a solution of my STP. If that minimum eigenvalue is negative, then this theorem of the alternative tells me how to restart optimization at the next highest instance of this low rank factorization. So I can continue optimizing to search for, I can continue the optimization. So all I have to do is just perturb my current solution slightly along the direction of this negative descent, second order negative descent direction, just to bump it off of stationarity. And I can then continue to search for an improved, I can continue to search for a solution to the STP. So the main thing I want to point out here is really what this is really a meta algorithm that tells me how I can do I can solve very high dimensional STPs by just solving a sequence of low dimensional nonlinear programs of the sort that look almost exactly like a heuristic local search for the original machine perception problem that I started with. But by wrapping them in this meta algorithm where I simply bump up the rank a little bit as needed, those few extra degrees of freedom give me just enough maneuvering room that I can escape from local minima and actually descend to recover globally optimal solutions, even for very, very hard machine perception problems that ordinarily would have a lot of bad local minima in them. And so 95% of the work that I'm doing looks just like the same sorts of heuristic local optimizations I'd be doing in heuristic local search-based stuff. So I preserve speed, computational speed, but I also get the benefit of provable global optimality when I'm finished, which is pretty neat. So, okay, so if you take all those things we've just discussed before and you stack them all together, you get an algorithm called SE-sync for robotic mapping. And this algorithm turns out to actually pretty straightforward then. So all I do is I apply this low rank semi-definite programming to approach where I just solve a sequence of these low dimensional nonlinear programs. That gives me a low rank factor for a solution to my STP. Once I've got that, I can use that low rank factor to compute the optimal value of the STP itself. And that STP value gives me a lower bound on the optimal value of my original estimation problem I'm trying to solve. So now I've got this low rank factor Y, but it may not have the correct dimension, right? Because I may have increased that rank parameter R. And so what I'm going to do is I'm going to, in order to get valid rotation estimates out of this, I'm going to project the blocks of this low rank factor onto the set of valid rotation matrices. And I can do that in a totally standard way, just using a singular value decomposition. That's a super cheap operation. To know how to do that in a closed form, that's very straightforward. And so ultimately, what that process will give me then is it will give me an estimate for my optimal vector of rotations, together with a lower bound on the optimal value of my original mapping or state estimation problem. And so if you look back at all the theory that we did in order to arrive at this, it's fairly easy to show that if my STP relaxation is exact, then this vector of rotations that I get is going to be globally optimal for my original PGO problem. And not only that, but I can check after the fact whether or not that is the case. And I can do that by simply comparing the objective value that this estimate attains for my original estimation problem. And I can simply compare that with the lower bound that comes from my STP. And in the event that this relaxation is exact, these two quantities will be the same. And that, in fact, provides a computational certificate of optimality for the estimate that I have in my hand. And that's because it attains this lower bound, and therefore it has to be optimal. So the punchline there is not only does it give me an efficient way of directly computing globally optimal solutions, but I can recognize a posteriori that the thing I have in my hand is in fact optimal, which allows me to distinguish for safety critical applications whether or not the estimate that I'm using for my decision making is in fact trustworthy. So I know before I try to drive down the Autobahn at 120 miles an hour that I know actually where stuff is, right? I know that I know where stuff is, not that I'm having to guess, right? Okay, so the story so far. So what I've shown you so far is how we can derive convex relaxations for post-graph SLAM. I've proved this relaxation is exact under bounded noise. And I've shown you how we can develop fast structure exploiting optimization techniques to solve these large-scale relaxations in practice. So the only remaining question then is a $65,000 question is, does blend? Does this actually work in real life, right? Does this actually work in a real life problem? So what I'm showing you here is an example of what this looks like when we apply it to a simulated grid pool. So I'm going to show you two cases. We're starting this from a random initial estimate. So I literally just randomly sampled some starting point. And I'm going to show you what happens if you try to apply an existing heuristic local search-based technique using just a Gauss-Newton method implemented in a library called GDSAM, which is commonly used for robotic mapping. And so basically what you're seeing here is that, because we start in a super bad local minimum, this local optimization just has a really tough time trying to disentangle this initial bad estimate to unfold it into the correct configuration. Now I'm going to show you a visualization of low-dimensional projections of the sequence of states, high-dimensional relaxed states that our convex relaxation approach goes through when we apply our relaxation-based procedure to that same problem, starting from the same initialization. And so what our stuff does looks like this. And so effectively what is happening here is because we have embedded our original problem into this much higher dimensional space, our algorithm is essentially able to exploit these additional degrees of freedom to sort of slide things past each other in a way that is not possible if you are constrained to the original sort of low dimensional configuration space that you started with. But the punchline basically is at the end of this, we were able to escape from these bad local minima and actually converge to a correct globally optimal configuration for this map. You can sort of see it actually unfold this into like the proper configuration. Okay, I know we're getting a bit short on time, so I think I might just kind of quickly go over these results. I mentioned before that this relaxation works under bounded noise. And so what we're showing in these experiments basically is what does that actually look like operationally? So here what I'm showing you is the relative suboptimality bound that comes from comparing the actual value of the estimate that we get with the lower bound that comes from our STP. And I'm showing you that relative suboptimality bound as a function of the angular noise, the translational noise, and the number of poses that are in the problems that we're trying to solve. And so the punchline here is you see that this is effectively flat at zero across all these different parameters. And so what that means basically, the punchline here is that our method is capable of recovering certifiably globally optimal solutions when the rotational and angular noise is up to, it exceeds roughly about a factor of 10 of what you would expect to see in a well-calibrated, realistic robotic mapping system. So what this is showing is this really does work under operationally realistic conditions. So these are simulation examples. But then you might ask, okay, does this work on real life data sets? So what I'm showing you here are quantitative measures that come from a family of large-scale SLAM benchmarks that are typically used to test the performance of large-scale SLAM systems. And so the things to take away from this is, number one, again, we see that we are recovering solutions that have, up to numerics, have a relative suboptimality bound of 0. So we're successfully recovering certifiably globally optimal solutions to these problems. We are successfully recovering certifiably globally optimal solutions to problems that involve tens of thousands of three-dimensional poses. So the underlying SDPs that are being solved here are on the order of about 60,000 dimensions for a three-dimensional problem like that one. These are quite large SDPs. And we are doing this by means of these structure exploiting fast SDP methods. We're doing this in a matter of fractions of a second, up to about 1 second, right? So compare this with the original thing that I showed you where it was taking 20 minutes to solve a problem that was about 100 times smaller than the ones being solved here. In fact, not only can these be solved in a matter of a few seconds, we can actually do this faster than generic local search methods if we're very clever about exploiting the specific geometry of these particular PGO problems in the design of our optimization techniques. So overall then, what have I talked about today? So the overall contributions from this then are this method that we produced, SESync, is what's called a certifiably correct method for robotic mapping, meaning that it's able to recover globally optimal estimates for moderate measurement noise, which is up to about a factor of 10 what you would typically expect to see in well-calibrated robotic systems. We're actually able to do this significantly faster than prior heuristic state-of-the-art techniques if we're very clever about exploiting the geometry of the problem to build fast optimization techniques. And in fact, this algorithm was actually the first algorithm to appear in the literature that is provably capable of recovering correct, that is, globally optimal solutions to the problem of robot navigation, which actually resolves about a 20-year-old open problem on the fundamental reliability of practical robotic navigation methods. And so if that had been it, I would have been pretty happy with this because we solve an important problem in robotics. But to me, the real significance of this work is that SESync was really sort of the prototypical example that showed that the idea of doing certifiable estimation by means of solving large-scale polynomial optimization problems globally is not just total science fiction. Like it's not a proposal akin to building a time machine, right? You can actually take these approaches and make them work with time and compute that is operationally relevant for real-time robotics applications on lightweight mobile robotic platforms. And so to me, this is really a proof of concept for a general class of moment relaxation-based certifiable perception methods that is much more general than just this particular problem. And in fact, subsequent to our original derivation of this result, there's been a bunch of follow-on work applying this same sort of relaxation or estimation strategy to a bunch of different problems, other fundamental problems in spatial perception, including things like rotation averaging, sensor calibration, multi-agent SLAM, and most recently range-aided SLAM. So I think in the interest of time, I will probably skip over some of these remaining examples and just conclude by saying that if any of this stuff sounds interesting to you, my collaborators and I actually have a chapter in the forthcoming SLAM handbook, which is going to be published by Cambridge University Press this year, that is all about certifiable estimation, certifiably optimal solvers, and theoretical properties of SLAM. So if any of this sounds interesting to you, I would definitely encourage you to check out the SLAM handbook as soon as it's available. There's a preprint that's available online if you're interested. So to conclude then, convex relaxation is great. Polynomial optimization is great. You should definitely try it out. And thanks for your attention. I'd be happy to take your questions.